Oh, there we go. Cool. All right, so let's start with this. How do I make this thing big? I forgot. Present, yeah. So I want to talk about how we're going to make a laser in WebGL, which is basically just GLSL, which is the shader language used to do shaders in any thing. I guess you can use HLSL, but don't, because, yeah. So I know that Unity uses GLSL shaders, GameMaker can, basically anything can. You can run it in WebGL too. This is what I'm talking about. I'm going to show you a demo in the browser. It's the exact same language. The only difference is that the WebGL stuff does not support some of the newer features of the GLSL language, but in general that doesn't really matter, except for loops are really annoying because you can't. No, it doesn't matter. Okay, so I'm going to talk about shaders. There's two kinds of shaders. Well, actually, there's three, but the third one doesn't matter because you can barely ever use them. There's vertex shaders, which is what's going to manipulate the vertices of a 3D mesh, and fragment shaders, which is what takes the output of the vertex shader and then renders it as pixels to your screen. There's also a thing called geometry shaders, which I think does like some kind of tessellation or generates geometry for the vertex shader, but I don't know what that does. I've never used it. We're going to do a demo with Shader Toy. It's a very easy way to play with fragment shaders, which is the type of shader that draws pixels to the screen. We're not messing with vertex shaders. In general, when you're drawing to the screen with a fragment shader, it's going to draw to the whole screen if you're trying to do a full screen effect. And what you're actually doing is you're taking and you're making a square out of two triangles and you're just drawing on that. And in fact, most game engines that are 2D actually just do that. They pass one square to the graphics card and they're like, please draw all these pixels on this square. So like, it's a full screen quad is what they call that. So I'm going to talk about two things real quick. UV coordinates, which is if you've ever done 3D mesh texturing, where you like unwrap a cube, you know, and it like, you take the cube and it unwraps into that like cross shape with like 6 flat things and you can draw on it and then it will texture that onto the cube. That's a thing called UV mapping. And in the UV coordinate system, it goes from 0 to 1, and that's just the percentage of how big the thing is. In Shader Toy, it passes in a thing called iResolution, which is the pixel value. You can pass that in yourself. Most engines will pass that in already, as well as a time parameter and some other stuff. Inside of WebGL, you have vectors, matrices, floats, ints. Matrices are basically just vectors of vectors. A vector is a in-dimensional thing, so it's an array, basically. But in WebGL, you can only do up to 4 dimensions. The reason is because that makes it really fast when they're doing math stuff. Yep. Oh, and you know, float and int. Floats are any kind of float.
So sorry, I have a question about the vertex and the frag shaders.
Yes.
So if you have an ocean,
Uh-huh.
which is going to have a vertex shader that's performing the waving,
Correct.
and the frag shaders showing the ocean
Yes.
visually.
Okay, so basically,
Code for both.
the fragment shader takes in all the vertices and interpolates data between each vertex it gets. So yes, the vertex shader runs first, and that's what draws the mesh. And then the fragment shader draws the actual pixels that got cut in the view frustum screen space projection.
Yes.
So, how to explain that a little better? So you know, if you have a cube and you take the cube and you put a flashlight and then the shadow of the cube gets put on a whiteboard, that shadow is the projection of the cube onto the whiteboard. And that's generally the use of a fragment shader. So the data that the data that the fragment shader gets from the vertex shader is this projection onto a 2D plane. If that makes sense. Okay. In fact, you can still do 3D math and raycasting with a fragment shader, but in general, because there is a Z depth buffer as well, but I don't mess with that at all, really, so I can't answer more questions than that. And then the last thing I'm going to talk about is easings. These are just math functions that take input and output, and it maps it to the input to the output in a different way. So what does that mean? So when you turn the volume up on your stereo, it actually increases logarithmically. So as you turn it up, it goes from the difference between 0 and 20 and between 20 and 40 are different amount of differences. Yeah, decibels. Well, I mean, decibels increase exponentially, but the volume increases logarithmically because you don't want to die. So, yeah, I just meant on the display on your radio. So, when it goes from 20 to 40, it's actually only turning the volume up by like 2 decibels. But if you go from 0 to 20, it's turning up by like 10. So that's a kind of easing, because you're easing the sound. So you're mapping this input and output. The reason that's important is because sometimes we want to take in stuff like the UV coordinate from 0 to 1 and output a thing that isn't linearly mapped to it. And I'll explain what that's doing in a minute. So easings.net has a lot of nice online examples. Tween.js has code samples of all of the easing functions you could basically want. And it's in JavaScript, but... Oh, no, I did not know that. Okay, well then do that. Don't look at Tween.js. Either way, the code there is so simple because it's usually just math. And then finally, there's this thing I found called desmos.com, which is amazing. It basically is an interactive graphing thing for multiple math functions at once. Yep, so now I'm going to show you the demo. We're going to make, as I said at the very beginning, we're going to make a laser. Not a real one, though, because I don't know how real lasers work. So what we're going to do is we're going to go over here to... First, I'm going to open up this thing. This is Desmos. So we're going to come up here to the top. Not that. Go away. And we're going to open this untitled graph. So I'm going to delete this function. And we have a function here, right? So this is a linear function. It goes in as 1. I don't know why this keyboard is open. It goes in as 1, comes out as 1. If we square it, right, x is increasing faster. So if we square it again, and then again, and then again, right? So this is 5, which is a quintic. And if you look on easings.net, there actually is an in-quintic easing. So the output increases kind of slowly, but then once you get close to 1, it starts increasing really rapidly. So why is that important? Well, if we draw this laser here, let me turn off the background, right? If we imagine the center point on the screen to be 0 on the y-axis, and then the top to be 1 and the bottom to be 1, as you go from 0 to 1, we want it to be very bright at 0, and then we want the brightness to drop off fairly quickly, but still have a fade, which is exactly what this is doing, right? So if we look here, let me make this code bigger so it's easier to read, extra large. You can see I have this in-ease here that takes in a float, and then this pow function, all it does is it does the input to a power, and then we're returning it. So right down here, you can see I have this thing called float y equals in-ease uv2.y plus f. The reason I called this UV2 is because UV typically goes from 0 at the top of the screen to 1 at the bottom of the screen. And I took it and moved 1 to the center and then divided it in half so that it goes from 1 to 0 to 1. And the reason why I want that is basically it's a trick so you can mirror the top and the bottom. Then, as you can see here, so actually if we just change this to y, I don't know what this will do. Yeah, you can see. So it's very intense at the very top, and then it drops off fairly quickly, and then it stays black all the way. So let's change this back. All right. So why is this purple? The reason is I define a color here. The colors usually go from 0 to 1, and it's red, green, blue. And the reason why I am overloading the number past 1 is I wanted the center of the laser to be white. So if we drop these to 1, right, like this, see, it's still kind of white, but let's change it to where the red is all the way up, and this guy's at like 0.5, and this guy's at whatever, it doesn't matter, 0.8. You can see that the center of it's just kind of like meh. So what we want to do is we want to basically, once you go past 1, it's going to just be white. So it maxes out, it caps out at 1. It's kind of like clamping it. Yeah, I couldn't remember the word there for a second. So the center of this is white here because we're clamping that at white, and then as it drops off, it turns purple and then finally turns to black. All this flux thing is doing here is Shader Toy gives you a value called time, and as you hit play here, you'll see that it's like wibbly wobbling in and out. So all I'm doing is I'm taking time and passing that into sine, and with sine it goes from 0 to, actually I'll just show you one here. Look at this, let's do this, sine x. Bam. Okay, well, we need to multiply that by a bigger number, so let's do 100. Right? Cool. Goes up and down real fast. Divided by 10. What? Okay, whatever. Sine x times 100 times 0.1. All right, so that's the sine wave, and you can see as if we pretend like time is moving us along the sine wave to the right, it's just going to gently move up and down and up and down and up and down. So if we're taking that and we're adding that to the intensity of the laser, it's just going to flux in this, or pulse in this really nice way. So the last thing I'm going to do is I'm going to add the ability to change it by moving the mouse around, which is an object that Shader Toy passes in. So I can click here. And we can go up to the top, and it should increase the intensity, and move down to the bottom, and it decreases it, right? Cool. So just to go through this code, it's literally, I'm just getting the mouse position. Shader Toy passes in the mouse position. Yep, right here. So yeah, it just passes it right in, and that's in a shader that's called a uniform. So if you're wanting to pass that in, you can actually calculate that in Unity and pass it into the shader as a uniform, and then you can do whatever you want with it. Like when you click the button, have an enemy's texture pulse blue, or I don't know what you would do with it, but cool stuff apparently. Yeah. Yeah. As you see down here, there's a time ticking. It's just kind of a timeline time. So if I hit restart here, it'll start from 0. And it's for most of the time, you just like pick the time that you started as 0. Whenever the shader loaded, you're like, that's 0, and then it just keep passing in the number as it gets bigger. Right, so let me just go through this real quick. We have functions, okay, they return floats. UV here, we're just calculating this thing called frag coord, which is, I don't actually remember what coordinates this is in, but you divide the frag coordinate by the actual resolution of the screen, and that gives you a value from 0 to 1. Resolution is the complete X and Y, frag coord is, the complete X and Y in pixels. The frag coordinate is the pixel coordinate, but sometimes we don't want a pixel coordinate, we want a percentage coordinate, and that's, most shaders you find will work in UV. Shader Toy, you should check this out if you want to learn how to do shaders. It's really easy, and there are tons of really, really cool examples on here that I look at and I'm like, I don't understand, but all right. So yeah, we calculate UV, UV2, we calculate the mouse UV. We have color here. And then to mix colors, there's a few things you can do. What I'm doing here is I'm multiplying the color by the Y value. And then finally at the end, I'm mixing it with this other channel that I'm sampling. So if I come in here and I change this to a new image, right? We can choose this. So what's happening in here is we're saying fetch the texture from the channel 0 and get its color and mix that color with the color we generated, and the amount we're mixing from texture 0 and texture 1 depends on this. So as y approaches 1, it's going to choose all the colors from the color we created. As y approaches 0, it's going to choose the colors from the texture that we input from the other channel. So you can actually, if we wanted to, we could take y and do this. So I'm gonna just do this here, and then change this guy real quick. I'm gonna copy and paste him. And then we'll just do this, copy that, and do that. And now it should choose the noise color. Oh, it didn't do anything. All right, well, I don't know why that didn't work, so whatever. Oh, yes, I do, because I need to put 1 here. Look at that. This is why you don't, see? So yeah, you can actually have it do all kinds of weird stuff. Yeah, so mix is a built-in function to GLSL. There are a lot of them. If you click on the little help button right here, it will tell you all the secrets. But as you see here, it has bitwise operators. Cool, don't use them because only WebGL 2 supports them, which means that almost no HTML game engine supports bitwise operators in GLSL, which is weird because JavaScript supports bitwise operators. I don't know, it's fine.
But that also means that it's like, it needs to have code directly into like, I think, OpenGL 3.2.
Yeah.
So the underlying pathway to get from that layer of WebGL into your actual GL code needs to be a lot lighter.
Right. It's everything's terrible. It's what I'm saying. No, it's not that bad. I'm sorry. Yeah.
So the fix function, is that how, like, some terrain systems, like, when the texture from
Yes.
the grass and the rock, is that how they do it?
Yeah. So what you can do there is if you want. So this gets a little complicated, but if you pass in a giant vertex array, this is actually how Phaser works. And the only reason I know this is because their thing didn't work very well, and me and James changed it. So what you do is you pass in this giant vertex data buffer that is actually not the vertices you want to draw, but it is sample positions from a texture like a sprite atlas. So you're like, oh, pick this. So the terrain example you're talking about, if you have a tile map, you can say sample this tile and place it at this position in the fragment shader. Sample that tile again and place it at this position. And then you can take that and then overlay other tiles from the same thing with an alpha mask as well, so that it will blend in the mix way that you're talking about. So yes, kind of. The other way you could do that is by simply passing in like 3 textures and then a 4th texture where each colored channel is the alpha mask for the previous textures, which is one of the suggestions I saw, which was like, just take a image and use red as an alpha mask and blue and green as a different alpha mask and then smash them all together and send it to the GPU. I'm like, I don't know what that image would look like, probably insane, but you can do it, apparently. Yeah, normals are kind of like that, yeah. Yeah, I guess that makes sense. Huh. I guess would it look, well, yeah, I'm imagining like 3 different masks just layered on top of each other. Okay, so I think that's basically everything. Did anybody have any more specific questions about this, or like why it works, or what it's doing, or why stuff? I'm gonna. Yes, actually, like, right. And some of the stuff is actually harder to do than it is in Photoshop. For example, we tried to implement a edge feathering blur thing. And to do that, you want to take a radial sample around the pixel and average the alpha values. But if you have to do that 60 times a second, and the image is like 512 by 512, and you're sampling a distance of 20 or 40 pixels, and you're animating it, and so that distance has to get bigger, and you're doing like, I don't remember, what did we calculate, like 450 million pixel samples every frame, or some insane thing. Yeah, it got slow is my point, so, yeah. Yep, that's all I got, so.